Hi, here I'm going to talk about machine learning combined with analytical science to optimize materials. Here, my name is Kenji Katayama from Chuo University, and this talk is about the optimization of the photoelectrochemical water splitting materials as an example. But this strategy itself can be applied for any sort of the materials or any sort of the phenomenon once you decided the target values and then analytical data of them. Okay, so and here I'm going to talk about at first this is the content, and I will talk about some general background of the data science and analytical science. I mean the measurement science, and then move on to the several applications, actual applications of the machine learning approach to understand the material for the material improvement, material development. Okay, so let me start from this one. Okay, actually, these days, data science has progressed rapidly, and then as many of you know, the AI has been anywhere in our daily life. And actually, many of the data science has a strong correlation, a strong influence on the analytical sciences because they have a good combination to study and then empower the performance of the analytical sciences. So I'm going to talk about some of the brief example for this. The first one is machine learning, and then the other one is optimization problem and data simulation and spectral decomposition. So as many of you know, the machine learning is most familiar AI technique, and then here's one of the example for the distinction of the cats and dogs by making the mathematical model to predict which one. This picture is cat or dog. And when we think about the analytical sciences, if we can obtain the spectra of the chemicals, and then we can categorize the different chemicals, right? So this is a categorization machine learning. And then if you want to know the concentration based on the spectra, that's a kind of regression problem. So regression function, right? So we can distinguish any sort of the spectra and connection with chemicals and concentrations. Looking at the optimization problem, so here one of the very famous problem of the knapsack problem. You have a knapsack, but and then you want to put several items with some features, in this case, weight and volume. And then depending on your purposes, you want to maximize the values inside the knapsack. So how can you do that, right? So when we think about the analytical sciences, we have various different chemicals, and then we have some analytical data for each of the materials performance. And then if you want to optimize the density, viscosity, or other chemical or physical properties, you can optimize it by using several different conditions, which is called regularization. And if you want to use pure chemicals, that's connected to the sparse modeling. And if you want to evenly distribute and many different chemicals you want to use, you can use max entropy conditions. The other example is a data assimilation. So this is not simulation. It is data assimilation. So this is a case when you think about, for example, the global warming study. So you have many different measurement data from airplane and on the ground and or ships or satellites. And then the information, this kind of information is used for simulation or using the physical model. And then you can tell the temperature, humidity of the earth. So when we think about chemical case, we have many different analytical data, such as concentration, temperature, and distribution. And then we have some models. And then you want to predict the reaction. Or and then in this case, so every step you have additional data, you can predict the future of the chemical reaction. So this is called a data simulation. This has been very frequently used in our daily life in the last couple of years because of the COVID. So you can check the COVID prediction. It's mostly finished now, but so every time we have some data of the COVID number, infection, the distribution, you can somehow the people can predict the future number of the COVID infection number, right? But this is exactly the data assimilation they do for to understand the COVID behavior. And the final example I want to show is the spectral decomposition, which has been used for a long time as mostly in chemoinformatics, such as the principal component analysis, PCA, and partial least square analysis, PLS. So what it did is, for example, we have the spectra of the mixture, chemical mixture, and then but looking at this spectrum, it's very difficult to understand what kind of chemicals are included and how much it is. And then we can do the mixture analysis by using these kind of the technique and to know the chemicals concentration and so on. So in this process, we use a clustering matrix decomposition and then dimension compression. So my point is there are many data scientific approach which is helpful to combine with analytical sciences. Okay, then move on to the real application what we did using the machine learning. So here the contents are our research recently. So at first, I'm going to talk about the why and then how different our machine learning strategy is for material development. So machine learning, as you see that it's the general structure is very simple. You have the parameter x, which is data, such as structure or parameters, and you have target property you want to optimize. And then the machine learning is simply correlate with this data x with y. Right? And then this has been used for example, in the drug discovery with molecules is represented by x, and the activity of the drug is y, and then y is optimized, y is predicted. And then in the reaction optimization process, you have different experimental parameters and then some reaction rate or reaction efficiency to optimize which experimental parameter is the best one. And then this kind of machine learning has been used for material informatics, where the chemical space, such as composition, elements, and the chemical formula and the structure is correlated with the target values, such as physical property or crystal structure. And then So in most of the cases, by combined with the DFT calculation to increase to understand the values and then also database, if you have, you can use it for correlation with the target value. But always there's a problem of the data number. Usually you need about thousands of data to apply the machine learning in many cases. That's why in the world research automation, so combined with robotic automation, and you can people are trying to increase the throughput experiment, so automatically the synthesize the materials or molecules and to increase the number of the examples. But when we think about the inorganic materials, there's a problem. So in the machine learning, so when we think about the molecule, for example, catalyst, we are interested in the structure and the selectivity correlation. And then if you have this kind of molecular catalysis, molecules are much easier to represent by number. So in any computer calculation, you need to convert the molecular structure or material to the number, right? So but molecules have a clear definition of for example, ring number, chemical species, molecular weight, lone pair, and so on. So easily defined by descriptors. But when we think about the inorganic materials, such as photocatalysts in our case, we've studied the light illumination on an electrode to induce the water splitting reaction. And then one of the famous material is iron oxide, Fe2O3. But can we define this one as Fe2O3? Actually, this performance is not only the chemicals, but also thickness, crystallinity, and then defect or impurity determine the performance. So it's impossible just describe this one as Fe2O3, right? So that's a problem. And also, when we think about the molecular catalyst, and then molecules are much easier to calculate to obtain the physical or chemical properties by the quantum chemical calculation. So easy to increase the data about thousand. However, when we think about these kind of material, especially in the research stage, still you need to prepare the samples, right? So it's difficult to increase the data in the lab scale. It's maybe around 100 is the maximum. So that's why we sort of will be helpful by using the analytical data directly of this material to represent this electrode, not Fe2O3, right? Because this analytical data definitely represents the samples you prepare. So that's why we use analytical data. And then we've developed a robust strategy to predict and improve the performance using the analytical data. Here, the water splitting material, our strategy is first device preparation and a performance analysis is made. And whatever it is, in this case, we use photo current and perform. So it's applied potential and current curve. And then collect the analytical data, various analytical data, and then these analytical data is converted into the numbers. So some feature values of the descriptors. And then the performance and the descriptor has been correlated by using the machine learning. And during this calculation, you can find the important part of the analytical data And then we can focus on that part to optimize the materials. And then this strategy has been started a couple of years ago. So what I want to say, this strategy actually works very well because analytical methods has been selected over a long history of research, right? So, and then the real resulting analytical data have a potentially effective descriptors for material. That's why the people use that analytical method, right? So that's
Okay, then from here, I will introduce some of the case studies about the by using this machine learning strategy. At first, let's start from case one. It's the performance prediction and the factor analysis of hematite for the anode materials. Hematite is one of the most famous photoanode materials, meaning that using the sunlight energy, this this induces the water splitting, so water to oxygen. And then, as you see, the iron oxide is rust. So you could see in many places the iron is oxidized to become uh, the brown color. Right? That's hematite. It is low cost, abundant, and chemically stable, and so and also it's brown color. So the have it has the visible light absorption, and typically this material is prepared by solution-based method. So the conductive substrate is um, uh, in inside the precursor solution and then heated up and then coating on the surface. And this is evaluated by the photocurrent value versus the potential applied potential. So and this value, so at some voltage, potential voltage, the photocurrent is the performance value. But as you see, the inorganic materials often have a variation of performance even under the same experimental condition. So what I mean is the here the photocatalytic performance had a large variation even for the same preparation conditions. That means what we did is we prepared a totally same experimental condition to prepare the hematite materials, and this is a performance. This curve is called IV curve, so potential versus for the current, and at 1.23 volt, which is the potential for water oxidation, and this value is the target value of Y. But in this case, experimental conditions are totally same, meaning that the X is same, right? So from same X to various Y cannot be predicted by using the function. So function itself cannot be um, generated like this one. So what we did actually is we collected analytical data for these materials, such as Raman, XRD, and UEVs. And from these analytical data, we generated the descriptors X, so analytical data X, and then predict the PC performance. So by using the machine learning. So it actually the we collected these analytical data like Raman spectrum, which correspond to the lattice vibration band of the hematite, And XRD button, obviously the facet of the surface. And the UV-based spectrum indicate the band gap and also um, internal transition. So these kind of the peak, if we can find the peak intensities and positions and wells, slope and their positions are collected, and they were changed, converted into X value as descriptors for machine learning. So here the X value for in this case we collected 46 features from the analytical data, and then for the sample of 75, and then the Y values are the photocurrent value at 1.23 volt, and these X and then Y are correlated with the machine learning as Y equal F of X. And of course, all the X values are not equally important, and actually many of them are not useful for prediction of the performance. And what we can select the important descriptors using various methods in data science. Here's one of them called the stepwise regression. And this is called the response plot. The vertical axis is a predicted value, and then a horizontal one is real value. So if the plots are on the y equal x, it means the prediction works very well. So by combination of different descriptors, we are going to predict the y value, and by changing these combination, optimize the y equal x, and then finally select the dominant important descriptors. And for the selection of the, for example, number and the combinations, we can use the Bayesian information criteria um, for model number decision. So which has been already kind of defined in the data science. So in essence, we can automatically select most of the important descriptors. And here's a selection of the important descriptors. And then here's a response plot for the true current and predicted current. And this R2 value is the evaluation criteria. And simply here I say determination coefficient R2 is the closer to 1 is means the good prediction. And then during this process, and it was about 0.9, which is quite high. Thinking about this model is made from the experimental values, and then 11 descriptors are selected, and then model is tuned by different regression models, and x y equal f of x. So during this process, in general, 80% and then 20%. So the data is separated, and then the first y equal fx is predicted by the training data set, and the score is evaluated by the test data set. So test data doesn't know the what kind of function is prepared, because, and then so it's a blind test. So by changing the training and the test data combination, the model is optimized, which is called cross-validation. And this is a very typical method to do the machine learning. And then by doing this, so in the training and then test data set, you could see the R2 value were about 0.8, F2, and H4, which were quite high. So and so it means that we could predict the performance nicely by using only the dozens of data. So what are the dominant descriptors? So we could find, for example, this part and this part has a positive and a negative impact on the performance. And this one is the near infrared region of the absorption, but mostly it's a kind of useless part because but when we think about this, it's a light absorption and scattering is involved in this baseline change, and possibly this is related to the surface roughness. And this peak is the not the band gap position people usually care for, but the internal transition. And we studied this carefully recently, and this kind of the internal transition band is affected by the morphology of the materials, and possibly this correlate with the morphology. So from the light scattering, sample roughness, internal absorption correlated with morphology change possibly. And also looking at the XRD peak, and there are several indications, but one of them I focused is 110 peak, which is uh, here, and this is a kind of no, here 110 peak. This is a minor peak, and we didn't care for much. But looking into the papers, some researchers mentioned that this peak has a strong correlation with the photocatalytic performance. And there are several FTO peaks are selected too, but possibly they are related to the sample thickness, but not much clear. And also in the Raman spectra, several peaks are indicated, but one of the unknown peaks, which is inactive peak for Raman, was selected, and then we didn't care for because it looks like just a background peak. But again, this peak was also suggested by some other research indicating that this peak correlated with the activity, meaning that this is Raman inactive originally, but in the amorphous condition, it's giving the peak. So, so again, here we didn't know many information in advance, but without prior information, we could find out several dominant descriptors in this case. So the take-home message from this research is, chosen descriptors are statistically likely, so but not necessarily always correct. So we have to carefully check each of them, and then they are good suggestion for you for your own sample for improvement. Okay. So next topic is the prediction for the inert hematite for the anode electrode. So here the machine learning prediction of the photocurrent, as I shown, for the training and test data set, so real value and predicted values. But you could notice that the data points are separated into the higher part and lower part, which indicate this one is a low photocurrent values, so meaning the low performance samples, and these are the higher performance samples. But we want to prepare these high performance samples, and the same in the test data sets too. So there's some reasons for the low performance, we suppose. So it seems like some are really active and some are not inactive. So we need, and then we sort of, there should be some information of the category. So in the machine learning introduction, we introduced the cat and dog distinction function by machine learning. And the previous example, we predicted the PC photocurrent values, which is called regression. But the we can do this for category prediction too. So maybe we can do the active and inactive category distinction by the machine learning. And same things we did using the same analytical data and then descriptors. And in this study, we added a more powerful analytical technique for the anode material, photoelectrochemical impedance spectroscopy, where during the light irradiation, so whatever we can obtain the electrical parameters for at interface, bulk, and a solution interface like this. This is the equivalent circuit we can model for these photoanode materials. So we can obtain the parameters of the R1, R2, or C2, or some like this. And then same things we did by the machine learning using the descriptors value, and this time we added the PEIS data, and then Y is predicted, but previously we predicted the number of the photocurrent, but this time is active inactive category prediction was performed. And then here is the result for training and test data set. So the categorization machine learning case, we can obtain the confusion matrix instead of the response plot. So what it means is this is real category and this is prediction category. So real inactive sample is if the is predicted as inactive, it's coming to this part, and the active one is predicted as predicted here. So this diagonal numbers indicated the correct prediction. So this one is incorrect prediction. For the training and the test data set, we could mostly predict nicely about the performance of the active and inactive category. And during this process, we can determine the dominant descriptors. And looking at here, the electrical performance, electrical properties are often selected. And then these R2, C2, C3 are general electrical properties. They are often used as general targets to improvement for the photoanode materials. So it's not much surprising, but then the things are one value. But this is the resistance hematite FTO, but they are not much care in the for some research of the photoanode materials, but it's a kind of really general thing. So the resistance is here, the hematite and FTO interface. So we studied at first FTO resistivity for these kind of the different materials, and you could see different color difference of hematite, but the resistance itself is not much different for different samples. But studying the temperature dependence of the FTO, actually FTO is degraded at higher temperature. So somewhere around here, the FTO might be resistance is gradually increasing, so that it's degraded. So we introduced the TL layer here to protect the FTO layer, and also FTL2 underlayer. How there's a research indicating that TL2 underlayer supports charge transport. And then what happened here is this is the PEC performance for the previous samples. So without TiO2 underlayer, by introduction of TiO2 underlayer, it's actually the quite better. And then as you see, here's the inactive samples. There are so many inactive samples in the original samples, but once TiO2 was inserted, the inactive samples are totally disappeared like this. And also the the other thing is average photocurrent value is obviously much improved. So was good. So what we could learn from here is that we focus on the spark, and then this one has been recovered, improved to remove the inactive sample. But also somehow some other the parameters also are improved, and also we found that some of the XRD peak was obviously enhanced by this. So somehow they're not only the target descriptors, other descriptors change positively, right? And we could come to the conclusion that hematite crystallinity has been changed to by this. So from this study, what we want to say is, the people usually care for some specific part, especially professionals. Professionals focus on some already know which part is important and then focusing on some part, and then they are mostly like, but you know you may unnotice some other important points, right? Like this example, because you take them for granted. The machine learning function um, suggests some important suggestions for the improvement. So the final example here is, well, here predicting an improvement of the performance of business boundary for an example. So the we want to improve the material performance as a from the experimental condition from the for the as a last target optimize this value. But this one is quite difficult because once you want during the material synthesis process, you want to change the synthesis method, and sometimes different equipment used and a different temperature given the if you change the temperature, if the reaction time also changes, and also as I showed in the example, that even under the same experimental conditions, the samples are different. So this direct prediction doesn't work well. That's why we added analytical data in between as an intermediate descriptors. So first, and then we want to once we discover the several important points, we want to correlate with experimental conditions with this. So what we did here is that for business validate hawks, which is one of the famous photoanode materials, to same as the hematite and low cost and more stable than the hematite, and visible light absorption about the band gap is about 2.4 electron volt, and a photo um, theoretical for the current density is about 7.5 milliampere, but still much lower than this. So the first things we did is do the same things in the performance analysis and then optimize the sample. The first thing is and the same things and this part. This sample is prepared by the metal organic decomposition namely the MOD method, which indicate the bismuth precursor and vanadium precursor are mixed and then spin coated and then calcinated, and these processes are repeated to generate the thin film. And then we did the analysis of each material by various analytical methods and target values photocurrent, and they are used as descriptors. And again, we use PEIS for the photoelectrochemical properties. And here are the descriptors we selected in the UV-Vis, XRD, Raman, and then PEIS. And we could successfully, again, photocurrent was predicted nicely using the experimental data, about 50 samples, and then our two values was um, 0.8, which is quite high. Thinking about this function was prepared by the experimental data. So photocurrent density could be predicted and then read from the 6 descriptors in this case. And they are the 6 descriptors we were selected. And one is the internal transition. And then this again, the near infrared absorption and a 211 facet and C2R2 values was selected. And then we suppose these may be controlled by the concentration and heating rate from our experience. So what we did is here for improvement of the performance, these dominant descriptors are connected with the experimental conditions. It's the second part. So there are many operational experimental parameters such as precursor concentration, number of layers, heating rate, heating time, temperature. We focused on the precursor concentrations and heating rate because this obviously color change gives a color change from our experience. And also heating rate is usually changing the crystallinity and homogeneity. So C2, R2 or particular facet can be modified by these experimental conditions. So we change these concentrations and heating rate. So here's what we could find that this is a UV-based absorption around 400 nanometer. Again, this is not a band gap absorption, and so this is an internal absorption band. And by changing the heating rate and the concentration, and this one was dependent on the precursor concentration. So as increase in concentration, this UV-based absorption also increased. And then looking at the PEC performance, again, same as this trend, that by increasing the concentration, PEC performance was improved. So this average intensity is an important descriptor linking the PC and the fabrication conditions. And then looking at the XRD peak 211 facet, which is here, that it's this minor facet. And then this one was controlled by heating rate and the concentration, like this trend. And again, the similarly PC performance was also controlled by like the same trend as like this. So we can optimize by reducing heating rate and concentration increase. So 211 facet is also an important descriptor connecting the PC and fabrication condition. And finally, the R2 value was also selected. R2 is resistance as the solution interface. And this one is positively correlated with, so resistance increased as the heating rate, and then the increased as the concentration smaller. So this is negatively correlated, and so heating rate is smaller is better, and higher the better. So again, the R2 also important descriptors. So this study tells you that analytical data that has originally, as I said, it's that decided from the long history of research, and then it has a good physical and chemical meanings. And the modification of these physical and chemical meaning, it needs our knowledge from our experience to manipulate these things. So with that, I will close this presentation.